Hi, hi everyone. I hope you are
Um minuto,
very well.
Débora.
What?
I think now you okay.
Okay. Hi everyone. I hope you are well, and thank you very much for your participation. Well, it's a pleasure to introduce Francisco Alegría. He's finishing his PhD at Universidad de la Frontera, and his doctor is with Juan Pozo, yes,
Yes.
and he will talk about the following working about some probabilistic properties of a non-local in time telegraph equation. Thank you very much, Francisco, for accepting the invitation. And you can start when you are ready. Okay?
Okay, thank you very much for this invitation, Deborah. I want to say first I'm a little bit nervous because it's my very first talk in English, so I'll try to do my best. And so right now I want to apologize for all my future grammar mistakes. And well, as Deborah said, the title of my talk, it's about some probabilistic properties of a non-local in time telegraph equation, and this is a joint work with my advisor, Juan Carlos Pozo, and the central topic of our work is to study this equation. This equation, it's called the non-local in time telegraph equation, and I'm going to explain why this is the name of this equation and my objectives objectives of this talk. It's show you why we want to study this equation first, and then show some probabilistic properties of the non-locals of the fundamental solution of this equation. So to understand this equation, I think first we need to understand what is a telegraph equation, and more precisely the classical telegraph equation. So here you have this very long cable. So we want to model what happens inside this cable. So this is actually a little bit a current problem because this cable exists in real world. Around the world, there are a lot of cables, and here, for instance, in United Kingdom, in UK, you have this very long cable. It's almost 400 kilometers, and this cable links connect the Scotland and England. And with this cable, these two countries shares some wind power because in Scotland there are a lot of windmills, so they produce a lot of energy, a lot of wind power. So they share with obviously with some agreement, but they share this power. And another example of this cable is, for instance, this cable links Greece with Israel, and passing through the Crete island and Cyprus island. And actually, this cable helps the planet, if you want to say in that way, because with this cable, this island, Cyprus island, it's connected with the central power of Europe. So they use less fossil fuels. So actually, I think this cable helps our planet. And well, there are a lot of these power cables. If you want to know more, or if you want to learn more about this, you can visit this website, and you can click here. Uh, and here appear a lot of this cable, and also appears this telecommunication cables. There are a lot of telecommunication cables. So we want to model what happens inside of this cable. So you can draw this very basic model of this transmission line. And here we have, with this circuit, we have some capacitance, we have some conductance, and actually this G represents the leak conductance. And we have this self-inductance, and we have some resistance here. So we want to model what happened with the current and with the voltage, the current through the cable. To understand that, we need to model what happened through the whole cable. But here you can take just some little or small slice of this cable, and then you have this input current, input voltage, and then you have this output current and the output voltage. So you want to model what happened here in this small slice. So what we have, this is actually a common or regular circuit. So you have you can analyze this just with the regular analysis of this circuit. So you can apply here, for instance, the so-called Kirchhoff Voltage Law, for instance, first. And what does we have here? We have, applying this Kirchhoff Voltage Law, we have the input voltage minus the current through the resistance passing through this cable, through this small slice, and minus this inductance here, and minus the output voltage must be equal to 0. So then you can model the situation, and then you can divide it by delta Z, and then approach this distance to 0, and here you can obtain this equation, which is the first Heaviside equation. Okay, and then you can analyze here in this node also with the Kirchhoff current law, and you can obtain pretty much the same situation, but you can obtain these two equations. Then with these two Heaviside equations, you can take the partial derivative here, this spatial derivative, and here the time derivative, for instance, and you can solve the system, and you can obtain this more general equation, where this U is representing the voltage or the current here. Also, if you consider some good enough materials, you actually can consider a very good conductance. So this G here, it's actually, you can consider this actually like 0, because this G represents the leak conductance. So this equation becomes this equation. And this is the so-called Kierkov telegraph equation. Okay, so let's look let's take a look at this structure here. We have this structure here of this equation, and then if you put here some positive constants, you have this another structure. But well, this is just for future calculation. It's not that important, this 2 and this square. But look, this structure. This is the so-called telegraph equation, classical telegraph equation. But with this model, you can, there are many situations not considered here. For instance, it cannot consider the what happens with the material at time, over the time, or for instance, the material wear or charge accumulation. I don't know, many situations. So you need to add some memory here to model a more general situation. So it's not a crazy idea. Consider some fractional calculus. So here you can generalize this equation in this direction. Well, there are a lot of direction to generalize this equation. You can put here alpha and alpha, and you obtain this equation. But also you can put here alpha, beta, I don't know, alpha plus gamma, and some other constant here, or other variable here. But we want to study this direction, this generalization. And here, this partial derivative, it's in the sense of Caputo, which is this definition. So this equation, Orsinger and Begin work with this equation, and this is actually in the literature named just like the time fractional telegraph equation. It's a generalization of the telegraph equation, and well, the time fractional is obviously for the fractional derivative. So Orsinger and Begin, with some conditions, with some initial conditions, obviously, they proved some result. For instance, they proved that the fundamental solution of this time fractional telegraph equation, it's actually a probability density function, which means the integral of the fundamental solution, it's equal 1, and it's a positive solution. So with that, they prove that there is a stochastic process associated to this fundamental solution, X alpha. It's the stochastic process. Then they proved also that the variance of this stochastic process is just like it's given by this formula, where this function is the so-called Mittag-Leffler function. It's a famous function, but it sometimes analyze this Mittag-Leffler function is not an easy task. So if you want to know the behavior, for instance, of the variance, you need to other. I'm sorry, there's something. No, never mind. You need some other theorem and other resource to analyze this behavior, for instance. Nevertheless, they proved actually in this paper that if you have if you replace alpha just by 1/2, you have the asymptotic behavior. You know the asymptotic behavior, and it's just like t to 1/2. And if alpha it's equal 1, the asymptotic behavior it's t to 1. Okay, so if alpha it's 1/2, the asymptotic behavior it's t to 1/2, and if alpha it's 1, it's t to 1. So we can ask ourselves what happens with the other values of alpha. 10 years later, in 2014, in 2014, Vicente Vergara proved that the asymptotic behavior for all alpha is just like also T2 alpha. So with, well, times some constants here, but essentially it's for alpha between 0 and 1, the asymptotic behavior is just like T2 alpha. Okay? So what does we have here? Look at here the structure. Look at the structure here. We have this, which is the classical telegraph equation, and then we have this, which is some generalization of this classical telegraph equation, the time fractional telegraph equation. So this equation also can be rewrite just like this equation. In this, with this g function, with this g function here, and we have here the, well, the solution. This symbol is the convolution. So here we have this g function, and here we have the same, pretty much the same thing with other convolution, but it's the same function. So again, we can ask ourselves, can we put here another function? And well, this is our equation with some other function here. This is our non-local in time telegraph equation. So this is actually a generalization of the time fractional telegraph equation. And the time fractional telegraph equation is actually a generalization of the fractional telegraph equation. I'm sorry, the classical telegraph equation. So this is also a generalization of the classical telegraph equation. Actually, this equation belongs to another more general type of equation, given with some measures, and you can obtain this equation from that more general equation. Well, this is the main work of Juan Carlos Pozo and Vicente Vergara in this paper. And well, if this is a generalization of the time fractional telegraph equation, can we obtain the same or pretty much the same result? Well, the answer is yes, we can, but with some additional condition, because this is a very general function. It's just a locally integrable function, so we need some condition on this k function. Well, here appear the condition PC. What is the condition PC? Well, if you have this locally integrable function, non-negative, non-increasing, and also there is another function such that the convolution between these two functions is equal 1, you can say that the k function satisfies the condition PC. But also you can write this that this pair satisfies the condition PC. Okay, this is it's an existence condition. So sometimes it's again not an easy task to know this function. Sometimes you don't know what is this function. But there's some theorems. For instance, in Jean Proust, in his monography, he proved that this definition if you have a completely monotonic function, this definition implies actually the condition PC. So if you have this condition, then you have the condition PC. And sometimes it's more easy to prove this. Okay? Well, with this condition PC, the authors prove that the fundamental solution of this non-local in time telegraph equation is actually a probability density function. The same conclusion. So with this probability density function, there is this stochastic process associated to this fundamental solution. So also they proved that with this they proved that the expectation of this stochastic process is actually the expectation is 0. And also they proved that the variance is given by this formula, where here appear this R function. And again, not always is an easy task solve this equation. Okay, so with this you can in order to obtain the same conclusions, for instance, we can ask ourselves what happened with the asymptotic variance of this asymptotic behavior of this variance. And for instance, we also can ask ourselves how slow this variance growth rate can be. In the literature, with these two kernels, you can obtain this asymptotic behavior, just like a logarithmic function. And this is the slowest growth rate known in the literature until last year. Okay, and this is actually a very interesting result, because in these two papers, the authors proved this asymptotic behavior, but with two different arguments. So they conclude the same result, but with two different arguments. Well, and here we have some natural questions. I think. And the first one: is there a pair in PC such that the variance grows lower than this logarithmic function at infinity? And this is our first main topic of our first paper. It's actually, this is my very first paper. And then we have some other question. For instance, this can we obtain a general formula for all the higher order moments of this process? Why this is a natural question? Because the higher order moments, what is some higher order moment? The first moment, it's actually the expectation, and the second moment is actually the variance. So Juan Carlos and Vicente proved that the expectation is 0, and the variance is given by this formula. So if we have these two first moments, the first and the second moment, what happened with the others moment? And then with this question arises another question. If you have this formula for these higher order moments, can we use this formula to learn more about the process? And well, this is the main topic of our second job, my personal second paper. So our contribution. First, I'm going to explain the answer of this first equation. Well, in order to answer this first equation, we proved we need some definitions first and some theorem. The first definition is this regularly varying function of index rho, which means that this limit it's equal to this power of x2 rho. And some special cases when this rho it's equal 0, we call this just like a slowly varying function. So with this definition, with this slowly varying function, if you have these two slowly varying functions, this is the it's actually a little bit famous theorem, the Karamata-Feller theorem. But well, roughly speaking, what does this theorem says? We have this. If you know the Laplacian form of the function close to zero, well, with some conditions here, but if you know the Laplacian form of the function close to zero, you actually can know the function. If you know the asymptotic behavior of the Laplacian form close to infinity, if you know the asymptotic behavior, you can know actually the asymptotic behavior of the function without the Laplacian form, but close to zero. On the other hand, if you know the asymptotic behavior of the Laplacian form of the function close to zero, actually, again, you can know the asymptotic behavior of the function, but close to infinity. So this is our main theorem to prove the following result. This is our main result of our first paper, and well, always we assume this condition PC. So if you have this, if the Laplacian form of this function is a regularly varying function of index rho 1 less than 1/2, then you can know the asymptotic behavior of the variance of the process close to zero. And with this another condition, if you have this another condition, you can know the asymptotic behavior of the variance close to infinity. So here, here, this theorem, this condition, actually seems a little bit unnatural. Why we put the condition on the Laplacian form of the function and not on the function? But we need to understand this property of the PC condition. First, by definition, if this pair is satisfy the PC condition, this is just by the definition, the convolution between K and L, it's equal 1. Then here you can apply the Laplacian form. So this convolution becomes a multiplication. So here it's actually very easy to solve this equation for the Laplacian form of L. So you can know an explicit form, the Laplacian form of L, even if you don't know what is L with this condition. So this condition on the Laplacian form of L seems a little bit unnatural, but actually it's not that unnatural. It's more easy actually. Okay. And here we have some sketch of this proof. Remember this formula. We have this, it's the formula for the variance of the process. Then here you can take the Laplacian form, and well, the Laplacian form of 1, it's 1 over lambda. And here, this is a formula for the Laplacian form of R, this R function. You can know the Laplacian form of R function, even if you don't know the R function. And well, obviously this is the Laplacian form of L. Here you can rewrite, or you can see that the asymptotic behavior of the Laplacian form of this variance is just like this expression close to infinity, where this function is actually a slowly varying function. So with this condition, we can apply the Karamata-Feller theorem, and then you can conclude our theorem, our formula, and it's in a very similar, with a very similar argument, you can find this close to zero. So you have this this result. You know the asymptotic behavior close to zero, and you know the asymptotic behavior close to infinity with this additional conditions. So here we have some examples. For instance, we have this the time fractional Telegraph equation. Remember with this g function. In this case, it's actually actually here you know the L. It's not an easy task here. You know the L function. So here you can take the Laplacian form of L, then you obtain this, and you can calculate this limit. And here we have this. This is our row 1, and this is our row 2. So satisfy the condition of our previous theorem. Then you can apply our previous theorem and obtain this result. And look at here, this result actually close to infinity. We have, remember, we have for alpha between 0 and 1, the asymptotic behavior is just like t to alpha. We recovered the result proposed by Vicente Vergara in 2014. So we have again the same result, obviously. It's a good thing. Well, we have some other examples here. For instance, the sum of two time fractional derivative. Here, close to 0. Well, we have just like t2 alpha and close to infinity. I'm sorry, close to infinity. It's like t2 alpha, and close to 0. It's t2 beta. We have another examples. We have this time fractional telegraph equation with this Mittag-Leffler weight. Those are classical examples presented in the literature. Well, we have this. This is the so-called time distributed order telegraph equation. And if you replace here by 0 and here by 1, you have again this Kochubey examples. Look here, if you put here just like 1, this is 1 minus 1 is 0, so this is t2 0, so it's 1. Here it's 1 2, so you have here this in close to infinity. You can recover the logarithmic behavior. So the asymptotic behavior here with this just like 0 and 1 here, it's just like a logarithmic function, which is the result present before. But we want something more slow. This is our question. If they are a pair such that the asymptotic behaviors. So this is we want something more slow. So here we construct some examples, some new kernels, and well, we proved some lemma, some corollary, some previous results, and then we proved this example. Actually, we construct these new examples, these new kernels. And well, we proved that there exists a pair in PC such that the asymptotic behavior close to infinity is just like this expression, where this expression it's the n times composition, if you want. This is for all n. So we call this very ultra slow behavior, because we can find this kernel to all n. So this is a very slow behavior. Well, close to 0, we also proved this result, but the interesting result is this part, this close to infinity. Actually, we proved something a little bit more general with this delta between 0 and 1. So here in some way we fill this gap between these behaviors. We feel this gap between this logarithmic function, this logarithmic behavior, and this t to alpha behavior. So we feel in some way we feel this gap. So we can actually apply this result with some different framework, with some different approach to this conclusion. If you consider this diffusion equation, actually the campaigner Sojander Vergara Sacker proved in this paper. They proved that the fundamental solution of this diffusion equation is also a probability density function. So there is an stochastic process associated to this fundamental solution. Also, they proved that the mean square displacement of this process is just like 2d times the convolution between 1 and L, where this d is the dimension of the space. So here appear the L function. So with our kernels, we can find some kernels such that the asymptotic behavior of the mean square displacement, it's just like this n times composition. So it's a very ultra slow behavior. So actually we can consider this, and the diffusion can be neglected. So it's a different application of, if you want, different application of our kernels. Well, this is our first paper, the main topic of our first paper. Now, what happens with the higher order moments? So we want to answer these two questions, and this is our second paper, my personal second paper, but this is also a joint work with Juan Carlos, but also with Veronica Poblete. And our first result, it's following. We actually found a formula for the higher order moments. We achieved this result. Well, remember the nth moment, or the moment of order n, we can calculate this moment with this formula. It's the integral of the fundamental solution of the. It's always with our non-local in time telegraph equation, the same equation. So we have the fundamental solution of the non-local in time telegraph equation, and here to calculate the nth moment, we can use this formula. And again, I repeat, this is the integral of the fundamental solution times this power of n to calculate the nth moment. So we proved that the formula, the nth moment, is given by this formula. Again, here appear the R function and the L function. Actually, if you replace here for just by 1, you can recover the formula to the variance proved by Juan Carlos and Vicente. You can recover this formula. So this is actually, and actually here you can recover the expectation, the first moment, and you can replace here by 0. So you have the first moment, and the first moment is the expectation, and it's equal to 0. So here you have this this result. Well, the proof of this theorem, of this lemma, it's a little bit tricky. We used some Laplace transform properties, some Fourier transform properties. Actually, we use this Fourier Laplace transform properties, and Actually, we use also the n times derivative formula, the Leibniz rule. Well, we actually find this formula for this moment of for all higher order moments. So we have this formula. What does we can learn with this formula about the process? Can we learn something about this process? Well, the answer is actually yes. Yes, we can. But here appears a little bit famous, I think, problem, which is the moment problem. More precisely, the Hamburger moment problem. Well, this hamburger is not the food. By the way, it's not like the sandwich theorem. It's hamburger is for German mathematician Hans Hamburger, I think. Well, here appears this hamburger moment problem, and what is this hamburger moment problem? Well, roughly speaking, if you know the moment, you know the distribution. This is roughly speaking. If you know the moment, you know the distribution of the process associated to those moments. To solve this moment problem, in order to give some answer of this moment problem to this moment problem, we actually prove this so-called Carleman condition. What is the Carleman condition? Well, the Carleman condition is if the moment satisfy this equality, if the moment this series is a divergent series, you can say that the moments of the process satisfy the Carleman condition. This is the Carleman condition. The proof of this condition of this theorem is basically realize that this inequality is actually true. We proved this inequality, and then we use some comparison test for divergence series. So we proved that this series is a divergent series. So this is a divergent series as well. And what does we have with this condition? What we prove with the condition? Actually, we prove that the distribution of the process is actually uniquely determined by this moment. So with this, we prove that the moment problem, the Hamburger moment problem, it's completely solved for the process for this stochastic process. So here we have actually the moments. The distribution can be determined by its moment. So here appear another. We want to know more about this distribution. So we proved actually we can again we ask ourselves if this moment generating function exists. Well, you need to prove first that the distribution is uniquely determined, and then you can conclude that this moment generating function exists. So what is the moment generating function? It's simple. It's just replace here this series replaced by the moments, and well this is just a formula, but we need some more closed formula, and we proved actually this theorem here, and well, we prove this this more closed formula But here appear this function s, and again, sometimes it's not an easy task to solve this equation. So this is a more closed formula, but we need some conditions sometimes to solve this equation. But we prove that this formula exists. And actually, we apply this formula for the classical case, and we recover this result proposed in this paper by Klensky. And well, this is a moment generating function in the classical case, the classical for the classical telegraph equation. And actually, we proved another result. The time fractional case. In the time fractional case, this case, this paper, this Orsinger and Begins paper in 2004. But actually, they didn't reach this conclusion. They haven't. They didn't reach this conclusion. But with our formula, we can solve this problem. We can find this more closed formula for the moment generating function. And well, here we can learn more about the distribution. You can use some techniques with this moment generating function to learn more about the distribution. And we conclude that this moment, actually the distribution is completely determinate. And well, this is some references, our first paper, our second paper, and some references here to understand or to learn more about these topics. So actually, that's it. Thank you very much. Thank you very much for this opportunity. Well, I don't listen. You're muted.
Could you listen now?
Yeah. I listen. Yeah.
Francisco, thank you very much for your nice talk. And I'd like to ask if there are some questions or comments. Could you see? We have one of Marcelo Almeida. I will put in the screen. Could you
Okay.
see?
It's possible to take alpha between 1 and 2. Yeah, but our focus, our focus here is to find out a more slowly behavior. So between 0 and 1, this represents some subdiffusion equation, and you miss some conclusions. But personally, I don't know the conclusions, but I know. Yeah, you can take the alpha between 1 and 2, but you miss some properties. So it's actually future work, maybe.
Okay. There is another question here. Could you see?
Okay, that's a good question. I don't know actually if we can prove this, but actually, as it's for all n, we don't have this lowest, because always we can add another term. You have, for instance, two composition, logarithmic composed with some logarithmic. You have the composition of two logarithmic function, but you have the composition of three logarithmic function, and you have the composition of four logarithmic function. This is because it's for all n, for all natural number. So we haven't the slowest behavior, but so I don't know if that answered the question.
Okay, thank you. Is there another question or comments? Giovanna, thank you. Giovanna put a comment that congratulations on your talk. It's so interesting problem.
Thank you, Joanna.
Like it, okay.
Thank you, Joanna.
So, again, thank you very much, Francisco, for your nice talk. So, I hope that you can see the presential form in Zoom, okay?
Yeah.
So if someone wants, we put a link here that if someone wants a certificate, okay, just fill this formulate here, okay? And it's just this. Thank you again. Bye.
Thank you again for this invitation.
Okay.
I can quickly